maybe we can get started. I want to start with two questions for you guys. One's more exciting, so I'll pose it second. The first question I have for you guys, and I'd really appreciate if anyone answers, this is literally personally just for me, which is, there's like, what, 90 people in this class, right? Roughly. There's probably 2 or 3 online. And yet you wonderful people are sitting here on your butts on these hard, uncomfortable seats. Why are you here? Why not just watch the lectures online? Like, what do you get out of the class experience that brings you back? Like, looking at the crowd, these are the same people I saw last week. Does anyone want to say why they're here? You know, you don't have to say, oh, I love being in class. You can just say, this is the reason I'm here. Because it turns out with like this chat thing and Zoom and all the online tools that education's changing like dramatically and quickly. So we have to be flexible and make better learning experiences to either accommodate people better or attract more people to class. But does anyone have anything that they like about being, even just one thing that you like about being in lecture?
The one, like looking for in lectures, that there are less distractions.
Yeah.
Because if I were to like attend it online, I'm more than tempted to open like a new tab and
that's right.
Watch YouTube. But that's where the book is actually.
Good.
I find it more engaging.
Okay. Yeah. Okay.
I am not here every day. There's some weeks where all my other classes are involved, so I just don't bother to come. So since I'm here anyway, I am here some days. I like being able to see answers face-to-face and interact with them and be able to yell answers at the class and just discuss that. That's something I can't do when it's asynchronous.
Yep.
And also, I kind of like the instructors in my class, like they want them to like show me and be able to interact with them.
Excellent answer. I guess one tip for you, since you guys gave me something, I'll give you something back. Oftentimes, as a professor, someone will email me, like in the last month of the last year, and say, how do I get into grad studies? I'm like, well, wouldn't it have been great if you had asked me this a couple of years ago? So if you're looking for tips to get into grad studies, obviously grades have some factor in it. And also try to get to know your profs, right? Like profs do research over the summer. Go up to a prof and say, hey, can I work on a project over the summer? That way, when you ask them for reference letters, they can talk about something other than, Sally got this grade in the class, that means this, and that's a really not useful letter to get for grad school. So anyway, the other question I have for you guys, which is maybe more exciting than helping me understand teaching, is so last week, this letter came out about regulating AI research. Did any of you guys get to see that? Hands up, who's heard of it? So some AI researchers, most notably led by Yashua Bengio out of Montreal, wonderful human being, really cares about society and the world, just a great person. Canada's AI ecosystem is largely driven by him. He's a really great person. He's very concerned about AI alignment and just slowing down research. And there was about 800 other people that signed it, including one person I found particularly fascinating that signed it, Sam Altman. You know who that is? CEO of OpenAI. Stop AI research, slow it down, says the guy leading the company that's 6 months ahead of everyone else. Anyway, I just wanted to know if anyone had any reactions to the idea of slowing down research, slowing down deployment. Good question. How do you regulate it? Yeah, it's a valid concern. Anyone else? Yep. Yeah, and things are changing with those labs, right? Like, if you looked at some of these labs 3 years ago, they would look a lot like the CS department, actually. Just a bunch of researchers writing papers. No one cares that it's monetizable in any way. Things have changed, right? Like they're now publishing less. They're now not saying what they're doing they're publishing papers that leave out all the key details. So yeah, we don't have a lot of insight into what's actually happening. Maybe one final reaction, and then we'll get into SARSA and Q learning, just as exciting as regulating AI research. Go ahead.
One suggestion was to control it at the level of CPU.
Mm.
That's what we do. Having connected CPU.
Turn down the compute tap. They are compute hungry. That's a question to think about when you're studying AI research. With that grand introduction, let's, yep. Oh yeah. I think this is like a song, it's never too late, it's never too late. Well, not you, because you're already a grad student. Come on, man. Yes, it's not too late. Any final reactions? I mean, SARS is pretty exciting. I'm excited. I wrote winter here, but I feel like it's spring, but I think technically the semester is called winter semester, so let's forget about that. Yeah, so this is kind of the picture we had in the videos. Like it's kind of like this flow here, right? We've got our input state, could be fancy things like images, could be boring things like position and velocity, but regardless, it's a thing that we can't learn a table over, or it wouldn't even be at all reasonable to do so. So we kind of pass it into our feature maker, so to speak. I know that this is a kind of a linear point of view, but so it gives you your features, and then you can do your semi-gradient PD, semi-gradient Q-learning, semi-gradient SARSA, and the semi-gradient thing just means, yeah, when we did the derivation, we kind of fudged it a little bit. I'm like, that part doesn't, zero gradient, it's fine. And so then we put the word semi in front of it to apologize for that. And then once you have that, we can learn our approximate value functions. And remember, our approximation is shown by, put a little hat on this, and we put the W as an argument to say, look, we're learning a weight vector or a vector of parameters, we sometimes say. And so last lecture was all about this box, right? We did some slides on it, we did some work problems, and now we're just going to talk about the fun part, which is once it goes through this thing, we're kind of back to a comfortable space, right? We have things flow into our algorithm has to learn a value function and pick actions. That's something you guys have been doing for months now. And so like I did the first lecture I gave you guys, I just want to quickly go through the videos and recap them. I'll ask you questions in red to spark your tongues, but I'll also invite you to ask questions like, yeah, I saw that video and it really annoyed me, or that animation was stupid, or I have a question. Anything like that is good. Yeah, so this was all about just going to episodic SARSA with function approximation. We've got TD, we know how to do TD with function approximation. So why don't we just do with action values and then wrap some exploration around it, and all of a sudden, congratulations, you have a control method. And so we call that on-policy TD control, or SARSA. SARSA used to have this really long, confusing name like modified connectionist Q learning or something like that. Doesn't really roll off the tongue, so I think it might have been Rich who coined SARSA. Anyway, kind of sounds like salsa. It's really fun. We talked about how to create state action feature vectors by stacking. Super, super simple. And then we just did some experiments with SARSA, which we'll talk about in the next couple slides, because I want to go through the learning curves, talk about what they mean. So is this an example of GPI? I don't know how much you guys talk about the GPI term in this course, but it's kind of the thing that's laid down in the dynamic programming chapter, right? This idea of having a policy that produces data, of making a value function about that policy, and then greedifying with respect to that, and then just doing that cycle over and over and over forever. So is that what's happening in SARSA? Are we learning a value function in SARSA? Yeah, we're learning a value function starts. Are we acting greedy with respect to it? Greedy-ish, right? So it has all the hallmarks of GPI, and that's the beauty of the GPI framework. Like, you don't have to go all the way to greedify your policy. You don't have to go all the way on each step of approximating the value function. We can take partial steps. Mountain car, what a brilliant problem. I spent way too much of my life solving this problem, looking at plots from this problem, and yet I still think it's interesting and relevant, at the very least as a pedagogical tool. Yeah, and this was just all about doing an experiment and seeing what a good experiment looks like. And so I do want to talk about that. So what a brilliant problem. We were too lazy to even draw it as a car. It's a box with wheels at the bottom of a hill, and you want to get up there, so what do? You just drive right the hell out. No, wait, underpowered engine. So what do you have to do? How do you get out of here? Yeah. So how could we encode a policy to do that? Does anyone know of like the really cheap policy to get out of here? Sometimes called the energy pumping policy. Yeah, so how can we turn that into like a really short line of code in Python?
That way,
Yeah, so we look at the sign of our velocity, and then we just take the action in the sign of our velocity. So if it's negative, we go that way. If it's positive, we go that way. And you pump your way out. It's not optimal, but it's actually like really, really, really good. And so this is why we like small problems like this, because we can think about, reason about, and even write down a simple policy. And then all of a sudden you can do things like, what if I just wanted to learn the state value function, V of S for this, for that cool policy? I could just do that and see what it looks like, right? And then I could compare that to the policy that I learned and how those value functions look different, which we will do in a second. Yeah, you're a car on the bottom of the hill, you want to get up there, blah, 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 transitions. -1 per step. What about at the goal? Do you give it like an apple pie or a big fat positive reward when you get there at the goal? No. Whenever someone says, in my cost to goal problem, -1, -1, and then some arbitrary reward at the goal, just say, don't do that. It's complicated for no good reason. It doesn't change the optimal policy, but it might contort what your value function looks like, right? So all we need to tell the agent is, life is pain. Every step is bad. So what's the purpose in life? Get up there and end the pain. Gamma is 0.1. It's an episodic problem. Position and velocity, which perfectly describes this problem. So chapter 3, we learned about MDPs. Does chapter 3 cover this MDP? No. Infinite state, right? We did finite MDPs in chapter 3, right? This is a continuous state space. But that's okay. That's like part of life in reinforcement learning. We have excellent theoreticians like Chaba working out all kinds of fun details for ourselves. And then a lot of times we have to step into a setting where, you know, our algorithm wasn't derived for, but the algorithms often extend and do reasonable things in practice. And that's kind of like the art and science of applied reinforcement learning. Oh yeah, and actions, right, left, and do nothing. So I don't know how much time you guys have spent staring at learning curves. I know you guys did an exercise question about why the learning curves bounce with TD, but this is like a fundamental communication mechanism for understanding reinforcement learning systems and presenting results to others. So it always follows the basic structure. And by the way, this is a tip if you ever have to give a presentation about how to present a plot. Only ever present one plot at a time, especially if it's the first one, and always present just the axes. Don't show the data because then people are looking all over the place. You want to explain what this is and what this is, and then show them the data. Anyway, these things usually have a usual way. Amount of experience is on the x-axis. So the more you go this way, the more and more and more time the agent has interacted with the environment. The more and more times it's tried to get out of the hill. In this case, it's episodes, so it's actually the number of times it's gotten out. And then you're going to have a performance number on here. A cost to goal problem -1 per step. The typical performance number is steps to goal, right? Or negative of the return in this case. And so learning curves usually have an exponential shape like this, right? You're really bad in the beginning, and then in fact, we just truncate the plot. And then as you get more and more experience, it gets better and better at the problem until it kind of plateaus out. Now, knowing Rich and remembering his like C++ code from like 25 years ago or whatever produced this, he would use pretty long episode cutoffs. So in Mountain Car, if your agent got unlucky, it might spend a really long time trying to wander out of there in the first episode. In fact, it's about 65,000 steps under a random policy to get out in Mountain Car. So a common thing people do in reinforcement learning when they run experiments is they set a cutoff. They say, don't let any episode be more than like 100 steps or 200 steps. Yeah. 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 It can get out of this problem under a random policy. You're guaranteed to do so. You're not guaranteed to see all the possible state action pairs because it's kind of like a spiral through the state space. There's certain combinations of position and velocity you just can't reach. I think so. Just make a really long time. But so if you cut off episodes really short, so in this case, Rich used about 10 or 20,000, which you usually don't bump up against that. But if you're cutting off episodes, say after 200 steps, it's actually going to change the problem you're solving, right? Because what happens when you have a low cutoff? Well, you restart the agent at the bottom of the hill again. And so it's kind of almost like giving it a new random chance to solve the problem. And so again, when I talk to you about these things, I'm going to give you guys tips for running experiments. And one of my tips is be cautious when you use those cutoffs because they can actually change your problem quite a bit. So it generally just helps with exploration. It's basically just giving you new restarts in the problem over and over and over. And especially in this problem, a lot of times when people implement it, there's stochasticity in the position at the bottom of the hill. So you're getting new randomness every time. And so my argument is basically when you introduce low cutoffs like that in cost of goal problems, you only make the problem easier. And it typically matters most for not great algorithms. So if you do these low cutoffs, you're going to make bad algorithms look better. And good algorithms will just work either way. But anyway, we have 3 curves here, and this is very, very typical. We've tried 3 different learning rates, and we see different shapes of these curves, right? The red one comes down fastest and gets to a pretty low place. Is this the optimal step size, 0.5 over 8? Maybe of these ones. And of course, this is the uneasy nature of experiments in reinforcement learning. How could we be more sure? I guess we could add 100 more learning rates. And we could even look at them and say, okay, the big ones are doing bad and the small ones are doing bad, and maybe the best one is somewhere in the middle. That would give us more confidence that we were near the good one, but we couldn't be sure, right? And in fact, every time you face a new problem, the best learning rate might be different. And so that's a little bit problematic, especially if your problem is Atari or Minecraft and your agent is really large and complicated and expensive to run, right? How do you try out 100 learning rates on a week-long experiment in Minecraft? That's really expensive, right? And so often people just don't do it. Does everyone have a basic understanding of like what these curves look like and what they mean? Do you have any questions about a learning curve? Does anyone know why there's an 8 here? That's weird. Remember the last worksheet question we like rushed through in high pace on a Fridays just to guarantee you couldn't absorb it at all? Remember we talked about the size of the feature vector? Remember we multiplied the feature vector by 2 and it made things bigger, and we said, well, we would account for that by changing the step size. And then we gave you that general formula about the norm of the feature vector and how it should influence the step size. That's exactly what's happening here. So tile coding, there's 8 tilings, which means there's 8 ones on your feature vector. And so we're scaling the step size by that because it makes it easier to tune the step size. It's easier to think about. Ooh, boys. This is a fun picture. Okay, yeah, so we want to look at the value function. But even in this small problem, the value function is kind of a complicated beast. You have a two-dimensional state space, right? Position and velocity. And then we also have like what the action we want to look at, right? Because this is the thing that the Q learning or SARSA is learning, right? The Q function. So the thing we're going to plot, and remember all the rewards are negative, so we want to make them positive, so we'll negate it, and we'll take a max because we actually just want to see the value function for what the agent thinks is the best action in every state, right? Like the value function for what the agent thinks is the optimal policy at this point in learning, okay? And so, of course, this is going to be some crazy surface. And ironically or acutely or amazingly, it looks like a hill, looks like a mountain. Isn't that convenient? Right? So we're plotting position and velocity and negated value on this axis, right? And so we're looking at steps to goal. So, you know, we want to be able to see where the start space is and where we end up, right? So what's the starting position and velocity? The starting velocity is probably going to be close to 0, I think. And the position is going to be the bottom of the hill. What's the bottom of the hill position? Does anyone remember? Yeah, it might be 0. Because I think it's like 0.6 at the top of the hill and like minus 0.5 on the other side. Okay? So basically what this is showing you is it's showing you the value through the state space, right? So, okay, we want this is the max of the Q value, and then we're going to negate it, right? So we want it to be few steps to goal. So this is going to be the way we get out. So we're going to start here, and we're going to wrap around the hill and come out this way, because this cliff is the edge of the position. So this is the edge of the world, right? So we can't go any further that way, and this is the back wall. And so why is there a big cliff here? Well, the big cliff is because here the velocity is too low based on where your position is, so you can't drive out from there, right? So there's like a discontinuity in the value function. And so this is where we're going to be getting out, right? Because this is where the top of the hill is, and this is where the velocity is high. So we're starting here, and we're like wrapping around this surface, and then we're driving out in behind out that way. And that's how the near optimal policy goes through this state space. And yeah, so that's where we want to get to. And this is where all the values are nice and low, because basically we've built up our momentum, and then we're slingshotting out of the state space and up the side of the hill. And that's that cliff that I talked about. And so you can sit here and you can stare at this picture, and you can think about where the start position is, where the goal position is, and that all these things make sense. And of course, this was after a long time of learning, right? 9,000 episodes. And if you look in the book, there's like how this hill looks during the first episode, after a few episodes, and you can see the approximation is doing the nice thing, which is early in learning, it's just like kind of like a big bump, trying to help the agent just get out in some approximate way. And it's only after a really long time of learning that you get this refined structure that's encoding the value function and the optimal policy. Yeah, and that's where we start. Right at the top of the hill, which kind of breaks my hill metaphor a little bit, but and there's our optimal policy to get out, or near optimal. And it makes sense, right? So we're going towards the goal, and then we're going away from the goal, and then back towards the goal, right? So we did our slingshot to get out. Why isn't it? Are you asking why it is not? Because our engine's underpowered, right? So it means we can't drive straight out. So we have to go all these animations, you pay the price later. You go towards the goal, and then at some point you can't make any progress up towards the goal anymore, so then you have to go back down the hill and go up the other side of the hill, and then once you reach the back side of the hill, then you can drive forward again because you built up enough momentum. Yep. the negative of the Q.
The action represented on it.
So we took a max on the action. So basically what we're looking at, we're only looking at the Q values for what the agent thinks is the best action in every state. And so the way I didn't mention this, and thank you for reminding me. You make this graph by just sampling positions, right? You say, I'm going to generate a bunch of X positions and a bunch of velocities, and then I'll query the value function in every one of those things, and that's how I build this heat map or grid, whatever we want to call it. So this is my plug for trying to get you guys to really care about this. And maybe I can do the slide in reverse order. This stuff matters. Like, there's ML engineers crawling on top of ML engineers, crawling on top of software engineers, all trying to get the coveted jobs and to be the superstars of AI. Being really good at experiments, understanding how to carefully compare algorithms is a super awesome skill. And I'll still declare that it's rare in industry. And it's also relevant, right? Like say you and your friend do a startup and you're thinking about different reinforcement learning algorithms you can use to rank resumes, something horrifyingly boring. You still need to know how to compare algorithms and understand them well empirically, right? Like that's just not something that's just for textbooks, right? So it's actually a really, really important skill, and it's not something that's focused on all over the world. In fact, I would say we always talk about U of A specializing in AI, particularly in reinforcement learning. I would say that U of A even more particularly specializes in good empiricism and running good experiments. And it's really, really important. And like when you think of just what we did, right? Silly, tiny problem. The one where we came up with a one-line Python solution to solve it, right? But we could still look at the effect of different step sizes. And I think Rich did 50 runs. 50 random seeds for each combination. We looked at how fast things learn. We looked at how good the policy was in the end. We even studied what the hill looked like, right? The value function. And that helps us understand what SARS is doing. That helps us understand what SARS is learning. That helps us understand the algorithm so that when you face the next problem, you know the things to plot, you know the things to look at, you know the questions to ask. And we should do this as much as we can, right? It's not just about a bake-off and what wins. It's about understanding algorithms, because no bake-off is complete, right? Like in a lot of ways, theory and practice are the same in this way. In theory, we make a bunch of assumptions and we make restricted statements about problems. In empirical work, we run some experiments and we just pray that it means something for some other problem, right? We can run a big battery of experiments. You can include all the Atari, all the Minecraft you want. You can open up the Dreamer v3 paper and then find that it still doesn't work on Acrobat, which is in the textbook, right? We'll never be certain that something works across problems. No empirical proof will tell you that. But understanding your algorithms will give you a much better chance. So become a good RL scientist and then get a good job. Then we did expected SARSA. I heard there was minor controversy in this course about how expected SARSA is implemented in the textbook, and that, as Chaba calls it, the lazy way of doing expected SARSA. Regardless, expected SARSA is a pretty cool algorithm. And of course, we can take our semi-gradient SARSA and change approximately 3 characters and get expected SARSA, or Q-learning, depending on what we choose, right? Of course, the lazy way. And I just wanted to walk through this algorithm because I find when I teach, it's useful just to step through these things and talk about what these things actually look like, right? Like this is somewhere in a notebook spread across multiple cells, but it's good to talk about in one place.
Sorry, can you compare how the parameter space look like the loss landscape for the higher coding function approximation versus like other like a neural network tends to, and like how whether like how smooth the loss landscape was for converging distance, or did you?
But I don't see if my graph is maybe record this video soon.
That's confusing. Fun. So what would you want to show with a loss landscape? Like when we think about loss functions, we often think about like, like a supervised learning problem, and you have like 2 parameters and you're looking at the loss and how, the agent is ascending on that loss surface, right? We don't typically do that in reinforcement learning because it's more complicated, right? So in my supervised learning setting there, that was a stationary problem, right? But so your loss is going to change based on the policy too, right? Which is changing on every time step also.
I see. So it becomes like kind of like a three-dimensional, like if the I see is the pole. Oh, I see. Makes sense.
Yeah, so there's a lot of analysis tools that we hope to import in that we don't, and you don't often see them in reinforcement learning, and it's not just because we're lazy. Like, it's actually more common. And as soon as you start trying to visualize things from higher dimensions, now you're projecting them down with like T-SNE or something, which means you can probably make it look like a rabbit or a lost surface or whatever you want, and then it's kind of, yeah. I mean, in some sense, we're getting insight about that by looking at the learning curve, right? Good question. Okay, so SARSA algorithm, you know, this function is just reminding you of the classic things you need to worry about when you're constructing an algorithm. You need to decide on your function approximator. That's the very first step. And like I told you 2 lectures ago, because that determines a bunch of other stuff after that. You know, most notably the step size, and in this case, the epsilon parameter if we're using epsilon greedy, right? And then of course, we have to care a lot about initializing our weights. And that kind of is important on 2 sides, right? On the linear function approximation side, if you're using tau coding, we know that we initialize this optimistically. Like we saw in the tabular case, you kind of get this nice systematic exploration, which is really, really effective, especially in things like mountain car. If you have a neural net, you better take care in initializing this because it really matters. And you guys can look at blog posts where you show like, initialize it to 0, no learning. Initialize it naively, really, really slow training. Initialize it with the fancy Xavier or whatever else people are doing, boom, hockey stick, right? Like these things matter. But life for a reinforced learning agent, especially SARS agent, is just a sequence of episodes over and over and over. You start in the initial configuration, you go until you hit the goal, and then you go again. And so that's what this is like, right? Initial start position. And then for each step of the episode, life is very, very boring. Take an action, observe the next state and reward. And now you have all the things you need for SARSA, right? Because we had SNA to start. And so now we have the rest of the word. Once you have the rest of the word, obviously you can do an update. And we just do our terminal update. I'm sorry, we don't do the terminal update. We do the regular update. And we do something different in the terminal state. And why is that?
Like you reach the goal, kind of.
Yeah.
There's nothing to compare it against, like the target.
What's the goal? What is the value of the goal state, the terminal state? 0. So that's okay. Then we should just be able to do this. Like, forget about this. We should be able to do this update, right? Because here, let's imagine S prime is terminal. We initialize our value function so that's 0, and then we'll be fine, right? What could happen? Generalization, right? So imagine I could magically reach into my neural network and say, make sure the terminal state is 0 upon initialization. And the neural network's like, okay, got it, Adam, because you know it's ChatGPT, so I can talk to my neural network. Okay, and then you do some learning. And then what do neural networks love doing? They do it on the weekend, late at night, every morning. What do neural networks do for fun? That's like their main objective in life. Generalize. They love to generalize. And so what's going to happen is if I could make this was terminal, this thing initially to be 0, I would do some updates, and then maybe I would go to a state that's near the terminal state. And the neural network's like, this terminal state now has a different value than 0. And then when you do your update, it's wrong. So we can't guarantee, in the tabular case, we could just initialize the terminal value to be 0. And because it was a table, there was no generalization. Every value was learned perfectly independently. We could ensure that that would stay 0. But in this case, with generalization, the generalization could pollute the value of the terminal state, and then your update would be wrong. And that's why we have to do this weird thing here of this checking. Am I at the top of the hill? If so, do this. And that's just like making this part 0, right? And then so if you're terminal, you go to the next episode. and then we start again. Otherwise, we do our update here, which is just updating our weights. And then we remember S and A, and we loop forever and ever and ever until we hit this terminal condition. Yep. You can try. I have a question about that at the end, so we'll talk about that when I get there. But the short answer is, seems like a good idea. Too bad. Too bad it doesn't work. How do you turn this into Q-learning? Max, right? Put a max in there. Change 3 characters. Exploration and function approximation. Thank you. Yeah, so this is hard whether you're in a banded, a tabular case, function approximation, holy bananas. Yeah, so it's just not easy. And so optimistic initial values, like we said, if you're in linear function approximation with tau coding, that makes sense. And I have a slide to try to explain why that's true. And yeah, we use epsilon greedy because exploration's hard. Not a lot of good answers, yeah? I perfectly understand. I have a slide with your question exactly on it. Don't worry. See? Nope, not this slide. I'm skipping this for now. Okay. So imagine our function approximator just had one feature. Okay, no matter where I went in this room, it just said, Adam, feature 1, no matter what I did. You know, I ate that desk, I licked a chair over there, I jumped on top of one of the TAs, same thing every time. Okay, one feature. And, you know, the 2D space, it's this room. Let's ignore the slope on the floor and all the other things. When you do something, whatever you do, it updates the whole thing, right? Because I only have one feature. So I'm sharing my value function approximation with this entire state space, right? No matter what I do, all the updates fully generalize, okay? We do something like tau coding in the same space, the generalization is local, right? So I've got my multiple tilings here, and these are the tiles that are activated by me standing perfectly in the center of the room. And so it's going to update the value function corresponding to all those states, okay? Sharing the value function update over the underlying state space. I wonder what happens with the neural network. Mind-blowing. Let's see. That's a thing. See how terrible that looks from the back. That looks fine. Maybe this was really, I don't know. Anyway, the point is that the generalization is kind of wild and nonlinear, and it's hard to predict, right? So this is local generalization. It's making updates to the values corresponding to states nearby you, okay, in this Euclidean space. This one's doing all kinds of weird things. It's like a global approximation. So maybe I'm up here. Local generalization means, you know, I'm walking up the stairs and I trip and I fall here, and now I decide around here is bad, right? That's local generalization. It doesn't matter that this is kind of flat and that was actually the step. The area around me is the bad place because I tripped, and tripping in front of the class is embarrassing. The single feature generalization would be, I trip anywhere in this room and I think the whole room is bad, right? Whatever I do in this room is probably going to be as bad as a trip. I know I'm being negative here. The nonlinear generalization is more complicated, but it also allows you to do things like, you know, maybe I trip in this room and it's bad in this room. What if I go to a totally different building? I should be able to generalize that in other buildings with this stupid step structure that I might trip and those states are bad. And so I don't have to relearn in every new building. I can generalize more globally about concepts. And that's what we're trying to get across with these kind of global generalization things, that it's more than just my current situation in the states, like physically nearby. You can learn general things. So this is very powerful and it's very, very useful for exploration. But sometimes we do want that global generalization to learn those cross-domain kind of things. But so why might this be very, very useful for our exploration? Yeah. So let's say red is awesome, right? It's chocolate ice cream, right? Everything is as good as chocolate ice cream. I trip on the stairs, you know, that's like pecan ice cream or something, some horrifying thing where they put nuts in ice cream. So, you know, around here is not great ice cream, right? But now I'm going to want to get to the other place. Like there could be something as good as chocolate ice cream up in the corner of the room. I should go up there and check it out. Whereas in this one, you know, initially I thought everything was as good as chocolate ice cream, and then I tripped, and then where do I go next? So this can be used to systematically explore the world, right? You're going to want to try to cover the whole place, and you don't have to cover it perfectly because you're generalizing. But that's the point. Oh, average reward. Oh, boys. This is a fun topic. So we've been doing discounting forever, right? Show you the value function. We show you the return. It's the infinite sum of future rewards. And you guys like threw rocks at Chab, and you're like, wait a minute, that could be huge. Could be unbounded. And then, you know, Chaba writes in gamma, gamma squared, gamma cubed. You're like, okay, whew. You know, you're all calmed down by that, right? Discounting. It's a thing we do. It's a way we handle problems when we don't have that episodic structure that keeps things bounded. And, you know, people make arguments like, well, if I offered you, you know, $10 today, or I said I'll give you $12 in 13 years, you'd probably take the $10 today, right? That's more valuable to you. Value in the future is discounted to you. But there's another way to handle problems that have, you know, one long episode or continuing as we call them, which is this average reward formulation, right? Which is a different way to formulate the problem and think about it. And the main thing I want to get across to you guys is that this is really understudied. Is it the ultimate solution to continuing problems? Can we throw away discounting and dance on its grave? No, but it's a new cool problem formulation. It's not that new, it's like 30 years old or something, but it's very, very underexplored, and it's a reasonable way to think about things. And the way I like to think about it is that you have some reward that you've been getting over the past little while, right? Your average reward. How have I been doing lately? And then when I'm making decisions right now, when I do something, how good is that new reward compared to the average? Like recently, things have been pretty good. So if you guys offer me $1, I'm like, that's just okay, right? But if something really cool happens, then you'll change. And it's all based in this average baseline, right? And so the interesting thing about that is you're looking at the difference between the average baseline and your current reward. So if you get something that's just as good as you've been getting all along, that's not that great. It's 0. And in fact, that's a way to think about learning systems that are persistently trying to make things better and better and better, because they're looking at how things compare to the average and saying, how can I take actions to make it even better than it's been in the last while? And so you can kind of think of it like a steady state system that's always trying to improve itself. So one of the arguments people often make about this that I don't find very pervasive is that, oh, but gamma is so hard to tune. What about gamma? That's why average reward is better. I don't really buy that argument, because we have introduced another hyperparameter here with average reward. And what was that? You don't actually have to tell me the Greek letter. The average reward algorithms need to estimate the average reward in some way. And so typically we do that with an exponentially weighted moving average. Everything you've been doing in this course, by the way, is an exponentially weighted moving average. Every value function you update has a step size, right? And so when we estimate the average reward, there's a step size parameter. We call it beta. Can't just set that to anything. That needs to be set thoughtfully. So we've traded gamma for beta. From a practical perspective, you can tell me which parameter is easier to deal with. Where are we? So when we were making all these videos, we get deep, deep into the course, and we're like, man, no one's going to know where on earth they are. People are going to ask the question, yeah, all that stuff about dynamic programming and NDPs, but what algorithm should I use? And so that's why we made these course map videos, trying to just map out just the content that's covered in the MOOC itself, right? This is not all of reinforcement learning. This is not all of reinforcement learning that Shibansh knows about. This is just what we covered in the course. So it's very, very narrow, right? But it's like a decision tree that can help you navigate the course. And it starts right at the top with whether you're in tabular or function approximation, and it goes down from there. And so the next question was just the one we just touched on, right? Which is, are we using average reward or not? Because they're different problem formulations. If you're in discounted NEPs versus the average reward setting, it's a different family of algorithms for each one. And then we talk about whether we're going to learn on each time step. Because if we are willing to wait to the end of an episode, then we might use a Monte Carlo method, right? Just wait and then make updates. If we're not, we're into the TD land. If we're doing a control problem, if we're not doing a control problem, we're doing some form of gradient TD. And if we are doing a control problem, we get their choice of the 3 algorithms we talked about. Again, just the algorithms talked about in the videos. The course map for the textbook would be much, much larger than this, right? We'd have all kinds of stuff in there. But we just wanted to give you an idea of how to navigate through the videos. See? I promised you. This is your question. All right, so we got one proposal. You take your state action, like you take your space, right? Like maybe it's mountain cars. So you sample random position velocities, and then you train the neural network to output a positive number of those position velocities and actions, right? That's one proposal. Anyone else have another idea of how to make a neural network optimistic? And if you have a really good one, we'll go write a paper about it. That's how this works. When you're studying a relatively young field, you can just come up with something in class, and they won't tell you, oh no, that was come up with in the 60s by Knuth. That doesn't happen in reinforced learning as much. Tile coder over the neural network. I mean, I'm picturing a neural network on its side and you just dropping a grid on it, so tell me more. Oh, tile code the outputs. Okay. And so, but we know the tile coding doesn't have the best scaling properties. So are we just tile coding the action values? Or are we tile coding the feature layer of the neural network? What are you thinking? We can't tile code them jointly though, right? That'd be too big. No, I mean like, it's going to be like a long vector, right? So we can't jointly tile code a big vector. I don't just like this idea. I'm just workshopping it with you. So, you know, what's our typical strategy when we can't tile code a really big vector? We just like tile code pairs of the vector, right? Maybe that'll work. Yeah. Yeah. Yep, so 2 neural networks is a common, not common strategy, but a strategy that people have proposed. We often think about one neural network is in charge of saying whether a state's been visited or not, and then the other one is used for learning the values. The name of the paper is called Alice and Bob or something like that. Terrible, because like, how do you search for that anyway? Write good names in your papers that describe what your paper's about. Yeah, so that's an idea. All these ideas are good, and maybe yours is most robust to the thing I'm going to say next, which is, so there's the initialization problem of the neural network, right? That it's like, it's hard to initialize it, but remember the thing I told you that neural networks do every day, twice on Sunday, every morning? Generalize, 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 right? And it's hard to control that generalization, and in fact, we don't really understand it, and the generalization is learned, which is even more mind-blowing to think about. And so, you know, let's say we take our first suggestion of initializing the neural network so that it outputs positive values everywhere. Then, oh my God, I'm gonna have to go through these transitions. What a nightmare. And so, you know, you've initialized your neural network. It's happy everywhere. It's chocolate ice cream all over the place. And then you do like one update and it's like, ha! this is what the world looks like now, generalizes in wild and unexpected ways. And so you can lose your initialization really, really, really quickly. And in fact, there's some nice papers out in the last year or so that actually shows that we train neural networks really slowly, right? We like make the learning rate like really, 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 really small, and we make it play Atari for an absurd amount of time. And so everyone thinks neural networks change very, very, very slowly, but that's not actually the case. And so there's nice papers out recently that show that actually like a lot of the neural network changes on every time step, especially early in learning. And so this kind of wild, uncontrollable generalization can happen and destroy all your optimism. But I do like the two-network idea. I do like using tau coding. We just have to be very, very careful about how we jointly tau code things to avoid like the exponential explosion. But this is like an awesome topic of research, and you should all think about it and make reinforcement learning a better place by solving the problem that's embarrassed us for maybe the longest. I don't know. You know it's bad when they create like a whole other field just to study exploration. Like, okay, those RL guys can't figure it out. We'll make bandits and help them out because those guys are too slow. That's why Chab is great. He's better than all of us, at least better than me. Okay, I think time's up. It's been fun. I'll probably never see you again. Enjoy the term.